Hello guys, today we'll build a JWT authentication service in Rust with Axum and then with Actix Web. This is a demo of what we'll be building in this video. In the Axum environment, we have the public view route, the get token route and the secret view route. We aren't signed in yet and we can access the public route, but when we try for the secret, we get an unauthorized response. We then have to get an access token for the user by adding their email in the JSON request body. We can use the token generated for this user and access the secret route once more, and we can now see the details of the user that owns this token. It works the same way when we switch to Actix too. We can view the public route. If we disable the access token, we get an unauthorized response. But when we enable this, we can get the details of the user that owns this token. Also, when the JWT expires, we get a message letting us know that the token is expired when we request the secret route. There are two major ways to achieve this on both Axum and Actix Web: using just the request extractor or combining the extractor with a middleware. Each of these methods has where it shines over the other. We'll learn all about this in this video. So guys, in this project, we'll create both the Axum and Actix Web applications in one cargo workspace. To do that, from your terminal, we'll create a new directory, which we'll call Rust JWT Authentication. We then cd into that directory. You can now open this directory on your favorite editor. We want this directory to be the workspace of our application, so we create a cargo.toml file, and inside this file, we specify this as our workspace, and as well list the packages we have as members of our workspace, which are Axum Auth and Actix Auth for start. Next, we create these two packages in our command line by running cargo new Axum Auth and cargo new Actix Auth in our terminal. We can now see the directory of these two packages from the sidebar. You may see a warning that says to update the resolver key in the workspace table to 2 to match the edition of our crates, since workspaces default to a resolver of 1. We can also see this warning when we try to run any of the applications. So we do that, and when we try to run again, the warning disappears. Now we install the dependencies for this project. For the Axum application, we will need Axum, JSON and the Tokyo crate. We then specify it for the Axum Auth package by typing --package Axum Auth. We want the full features from Tokyo, so we specify that by adding --features Tokyo/full. We then run this command and it installs the crates and updates the cargo.toml file. When we check our cargo.toml file in the Axum Auth package, we see that those dependencies were added to the file. You can copy these from my GitHub and paste it directly in your cargo.toml file to use exactly the version I used. But use the command line if you want the latest versions. I will drop my GitHub link in the pinned comment and also in the description. For our Actix Auth package, the crates we need are Actix Web and JSON. We will specify that this is for the Actix Auth package by adding --package Actix Auth. When we run this, it installs our crates. After that, we can check our cargo.toml file to verify that our dependencies were added. We can open up the main.rs file in the Axum Auth directory. The first thing we'll do is to make this asynchronous, and we have to set an async runtime by wrapping this with an attribute macro from Tokyo called main. One good to know about this attribute macro is that we can set if we want this project to be single-threaded or multi-threaded, and define the number of worker threads we want to spawn for our server. This defaults to the number of CPUs you have on your system. We will set it to 4 for this project. Now it's time to set up the Axum server. The first thing we'll do here is to construct our routes. To do this, we get the router struct from Axum router and call its new function. Be sure that Axum router is imported from Axum. We then specify our routes by calling the routes method and impute the path for the route. Next, we call a method router function. This can be a get, post, patch, delete or more. We want to set up a get request for this route. Therefore, we go with the get function, and this should be imported from Axum routing get. We then pass in our handler for this request. For now, our handler will be a simple asynchronous function that returns a string. We do the same for the get token and secret view routes. Our get token route will be a post request. We update the return strings as well. Now we set up a TCP listener. We get the TCP listener struct from Tokyo, call isBind method and pass in the address we wish to run our server on. Please be sure the TCP listener struct is imported from the TokyoNet module, as the standard library also have a TCP listener with a bind method, and this could lead to hours of debugging. The bind method is an asynchronous function that returns an I/O result containing a TCP listener. So we await the result and call the expect method. If the address is already taken, the bind method fails, so we pass in an appropriate message in the expect method. Next, we serve the application by calling the serve function from Axum. This takes in our TCP listener and routes. It's an asynchronous function that returns a result as well. We can now run our application and test the routes. This specifies that we want to run just the Axum auth binary. So when we access the public view route, we get the public view string returned to us. And so is the get token route and the secret view route as well. We will now work on making this route return a proper JSON. For the public view route, we replace it with a new handler which we will name public view handler. The public view handler will be an asynchronous function that returns an Axum response. This response type is gotten from Axum response module. We want to return a JSON with a success field of Boolean type and a data field which contains the data or error we wish to return. To do this, we first call the builder function from the response struct. This returns a builder struct from the HTTP crate, which we can use to construct our response. Let's visit the Axum documentation, and we can see that this builder function returns a builder struct that has a status method for setting the response status, a header method for setting the response header, and a body method for the body of the response. Back into our code, we call the status method to set the status code of our response. We then pass in an OK status code by importing the status code enum from the Axum HTTP module and choosing its OK value. We can directly pass 200 as a number into this, but we shall leave it this way for readability. We want to specify that the content type of our response is a JSON. So we add a header to our response by calling the header method. We can type out content type as our key, or use the header enum from Axum HTTP and choose the content type element. For the header value, we use application/JSON. We then set the body of the response, which will be a JSON string. The body method doesn't accept the setDate value returned from the JSON macro, so we call the toString method after the JSON macro to convert this to a string. The body method returns a result which fails if one of our response constructions fail. Although this is not going to fail with the values we provided, we call the unwrapOnDefault function to return the default response when it fails instead of panicking. We have some errors in the function. This is because we have to specify the type of our response body. We send a string in our response body, so our return type will be a response with a string type. We can now test our public route. We see that we have a JSON with a success and data field returned, and our response comes with a 200 status code. And when we check our header, we see that the content type is specified for JSON type. Moving over to the getToken route, we remove our previous handler and replace it with the getTokenHandler function, which we shall define below. We can use a to-do macro in the body of the function for the main time. In our getToken request, we need to send a JSON containing the email of the user in the request body. Our getTokenHandler will then extract the JSON from the request body and generate a JWT token for the user. This token will then be used in the secret view route to authorize that user. We need to create a JWT encoding and decoding function. Since this function will be the same for both the Axum and Actix auth packages, we define this in a separate library crate, which can be imported from both packages. We shall call this library JWT lib. We can see that a directory with the name JWT lib is created in our workspace root. We can also see a warning about invalid workspace configurations. So we open up the cargo.toml file in our workspace root and add JWT lib as a workspace member. Now we need to install the dependencies used in generating our Json Web Token into our JWT lib package. So in our terminal, we write cargo add chrono, which is a crate for manipulating date and time in Rust. This will be used to set the expiry of the JWT token. Next is the Json Web Token crate, and lastly, the sedded crate for serializing and deserializing Rust structs. These crates are for the JWT lib package, so we specify as usual, and from sedded, we will need the drive feature to enable structs to drive the serialize and deserialize traits. Enable these by adding --features sedded/drive. We then run the command, and this installs the crates and updates the cargo.toml file in the JWT lib crate, which we can confirm by inspecting the cargo.toml file of the package. Now it's time to create our JWT encoding function. So we open up the lib.rs file in our JWT lib package. We will clear out the content of this file and begin creating our encode function. This should be a public function, and we shall name this getJWT. This function will take a user struct gotten from the JSON passed in the request body and generate a JWT for that user. So we add a user parameter of type user as an argument for this function. We now need to create the user struct. This struct will be public, as we will need to import it from other packages. The user struct should contain an email field of type string, and this is what we'll use to create the token for that user. In a real-world application, there should be a password for verifying the user, or the token will be sent as a magic link in the user's email. But for simplicity and keeping this tutorial on point, we shall skip the password or email verification. Since this struct is coming from the request body, it needs to derive the deserialized traits. So back to the main.rs file of the Axum auth package. In the getToken handler, we extract the user struct from the JSON in the request body. To do this, we add the JSON extractor from Axum in the functions argument and extract the user. This will be a JSON type and its target will be the user struct we defined in the JWT lib package. To import this struct, we need to add the JWT lib as a dependency in the cargo.toml file of the Axum auth package. We have to specify where cargo we get this crate from, and this can be found one directory above this cargo.toml file. Now we can import the user struct from JWT lib package. We shall do this for the Actix auth too. Back to the lib.rs file in the JWT lib package, we want to generate a JWT token for this user. Every JWT token needs to have an expiry and maybe some additional validation to it, like restricting a token for a different group of users such as an admin. For simplicity, in this project, we would only like to have a sort of expiration for each token. Let's visit the encode function docs in docs.rs. We can see that to encode a token, we need a header, claims and an encoding key. The claims is a struct that contains the data to be encoded to JWT, along with some fields for validation. If we look at this readme from crate.io, the claims struct should derive the serialized and deserialized traits and can have validation fields of the following. We will just set the exp field, which is a UTC timestamp of when our token will expire. All the fields set here will be used in validation when decoding the token. Back to the encode function, we can see there is a header where we can set the algorithm we will use in encrypting the claims. By default, this uses HS256, which allows us to encode and decode using the same key. Using RS256, we encode the token using a private key, while we decode the token using its respective public key. That being said, our claims struct will have an email field in which we'll pass the user's email and an exp field of type i64. We resume defining the getJWT function. To get the token, we call the encode function from the Json Web Token crate. We will use the default header, which we will also import from the Json Web Token crate. We will pass this user's email into our claims. To make the demonstration easy, we set up the Json Web Token to expire a minute after it's created. To do this, we first get the current UTC timestamp by importing the UTC struct from chrono, calling its noun function, and then add a minute time delta by calling the minute function associated with the duration struct imported from the chrono crate. We then retrieve the timestamp. For the encoding key, we import the encoding key struct from the Json Web Token crate and call its from secret function. We then pass in our key, which I will set as my key, and since the secret should be a byte slice, we call the asBytes method on our key. Our token variable here is a result enum. We will have to make this function return a result whose OK and error values are both strings. Therefore, we map the error into its string and return the token. Back to our main.rs file, in our getToken handler, we get the JWT token of the extracted user. If it is successful, we will return the JWT token to the user, but if it's not, we have to return the error string. So we match the token, and if it's successful, we build up our response as we did for the previous handler, and the data field will be an object that contains the token field. For the failure case, we change the status code to bad request and success to false. The data object will contain a message field that holds the error string. We will now rerun the Axum Auth application and test our API. In the request body, we add a JSON with the user's email we want to get a token for, then run the request. We can see the JWT of the user in the token field. The next feature we will implement is to get the details of the user with this JWT token from the secret view when we pass it in its authorization header. This is where we will implement our request extractor. In the main function where we define the routes, at the secret view route, we update the previous handler with a secret view handler function, which we define below. The secret view handler function will return a response with a body of type string, like all the other handlers. The secret view request will contain an authorization header, whose value is a string that begins with a bearer, a space, and then the JWT token. From the request header, we extract the user that has the token and returns their details in the response. To do this, we create a custom extractor and extract, just as we extracted the JSON body in the getToken handler. As we can see from the Axum docs, you can define a custom extractor by implementing the fromRequest path or fromRequest trait for the struct we want to extract into. You should implement the fromRequest path trait if your extractor does not need to access the request body, and implement the fromRequest trait if it will consume the request body. Since we are getting the token from the request header and not the body, we implement the fromRequest path trait. We wish to extract the token into this user struct. Normally, we will implement the fromRequest path trait for the user struct, but since we would use this struct for both Axum and Actix Web, and this struct lives in the JWT package, it's best to keep every implementation in its domain. Therefore, we will create a wrapper struct around the user struct, which we will call auth. And we will implement the fromRequest path trait for the Axum struct. We will create a similar struct and implement an extractor trait on it for the Actix auth package. To implement the fromRequest path trait, we first add the async trait macro from Axum, and then add an implement block with a generic which we will name S. S should implement the send and sync traits. Looking at the documentation for the fromRequest path trait, there is a required type called rejection and a required fromRequest paths method. The rejection type is the type that is returned when the extraction fails. When we try to extract the user from the JWT token and we fail, we want to return a response to the user with the error message in JSON form, So our rejection type will be an Axum response with a body of string type. Next, we define our from request paths function. This should be asynchronous and return a result with itself as the OK value and the rejection type as its error value. The arguments of this function are the request paths and the state. So we add that we will import the path struct from the Axum HTTP request module. We won't make use of the state, so we put an underscore in its place. We will have to extract the access token from the request header. So we get our access token variable from the paths.headers.get. This returns an optional header value. We will have to convert this header value to a string if it exists. So we can separate our token from the bearer, since when using JWT, our request authorization header will be a string that starts with a bearer, a space, and then our token. We use the and then method to convert the header value to a string if it's some value. Next, split the string and take the token portion from the second index. This returns an optional string slice. The access token variable will be known if there is no header, there was an error converting the header value to a string slice, or if the token isn't a space after the bearer. We then perform a match operation. If the access token is none, we return an unauthorized response to the user. But if it exists, we decode the user from the token. For the non-arm, we return an error that contains a response with an unauthorized status code. The success field will be false and the data will contain a message that says, "No token provided." We will leave the sum arm with a to-do macro for now and define the decoding function for the token. We will have to define a decode JWT function in the JWT lib package. The decode JWT lib function is the opposite of the get JWT function. We will take in the token string slice and return a result whose OK value is a user and error is a string. To get the token data, we call the decode function, which will import from Json Web Token. We pass in our token, and our key will be the same as the key we used for encoding the JWT. Just as in getJWT, we import the decoding key struct and call the fromSecret method and pass in our key string as bytes. Since we used the default header when encoding and our claim struct only has an exp field, we can use the default validation struct. We need to specify what struct are we decoding the token to. So before the parenthesis in the decode function, we add that the token data is of the user struct. We can see that the token data variable is a result that is either a token data with the user struct or an error. We need to extract the user from the token data, and if there is an error, we need to return the error string. So with a match operator, we extract the claims from the token data. This is the field that holds the user struct. For the error, we convert it to string. Back to the trait implementation, we get the user from the access token using the decode function we just defined. Recall that this function returns a result. So with a match expression, if decoding the user is successful, we will return an OK value that contains the auth struct wrapping the user. If it is unsuccessful, we return an error result similar to what we have for the non-arm. But the message field will contain the error string returned when decoding. The auth struct is now an extractor. Adding this in the function argument extracts the user from the token. We can now return a response with the user's details. The status code will be OK, the success should be true, and the data should contain the user's details. We are getting an error because the user struct cannot be serialized to JSON. We derive the serialized trait for the user struct. We can now test our secret view route. When we run the secret view route without passing any token, we get a failed response. And the message field tells us that no token was provided. We then get a new token from the getToken route and use it in the secret view route. When we run this, we can now get the details of the user that generated this token. If we modify this token, we get a failed response that says invalid token. We set this token to expire after a minute, but this will take 60 more seconds to expire because by default, validation adds a 60 seconds leeway when verifying the expiry of a token. We can modify this leeway just as in this example from its documentation. After 2 minutes, when we try to access the secret route, we get a failed response and the message field tells us that our token is expired. It is now time for us to quickly rewrite this in Actix Web. We copy the main function from Axum and paste it into our Actix Web main.rs file. For Actix Web, we replace Tokyo main proc macro with Actix Web main. The main function in Actix Web should return an IO result whose OK value is an empty tuple. In the body of our main function, we import the HTTP request struct and call its new function. This accepts a closure and we will have to move the ownership of the variables used into this closure. We then import the app struct and call its new function to initialize the app struct. This is where we define our routes. We define our routes by calling the .route method and passing our parameters. We call the get function from the web module of Actix Web and pass in our handler in its .to method. We do the same for the getToken and public view handler. We shall define these handlers later. In Axum, we specified our worker threads to be 4. To do that in Actix, we call the workers method and pass in the number of threads we want the application to run in. We then set the address we wish to run our server on using the .bind method. This returns a result, so we can call the expect method with the message we want to print to the console if this panics. We then call the run method and await. Be sure to import your modules correctly. We copy our public view handler from Axum into our Actix Web package and modify it. in place of the response struct from Axum. In Actix Web, we use the HTTP response struct, which we will import from Actix Web. The HTTP response struct from Actix Web comes with some methods that reduces the amount of code we use to return a response with a JSON body and a status code. To return a response with an OK status code, we call the OK function from the HTTP response struct. We have one for bad request, internal server error, and every other status code. All this returns a HTTP response builder struct in which you can build our response with. Instead of adding a content type header and then the body to return a JSON response, we use the JSON method from the HTTP response builder struct. We will have to import the JSON macro from Sede in this package. We can pass in a JSON value directly, so we remove the .toString method. And since this method just returns the HTTP response struct, we remove the unwrap or default method. We can comment the other two routes we defined after the public view route, so we can test the handler we just created. From our terminal, we enter cargo run. We have to specify that this is from the Actix auth binary, so we write --bin Actix auth. I will switch to my Actix environment on Insomnia, which runs the URL variable on port 2424. And I get the response we got for Axum. For the get token route, we can copy our implementation in Axum and convert it to Actix as we just did. We can now convert the return type and the body of our function just as we did for the public view handler function. We will import the JSON struct from the web module in Actix Web and the user struct from our JWT lib package. Remember, we have to add the JWT lib package to our list of dependencies as we did for Axum. We run our code, and when we test, we can see it's working as expected. Now we do the same for the secret view route. We will create an auth struct wrapper for the user struct as we did for Axum. We will also need to implement an extractor thread for the auth struct, so we can copy that of Axum into our file and start to modify. We won't need this for Actix. The extractor thread for Actix Web is the from request thread. The required types are the error and the future types, while the from request method is the required method for this thread. We will have to remove the generics and replace the from request paths threads with the from request thread, which we import from Actix Web. We then rename the from request paths to from requests and remove the async keyword right in front of it. The two arguments of this method are the HTTP request and the payload. We won't need the payload for this function, so we use an underscore as the variable name. We import the HTTP request from Actix Web and the payload from the dev module in Actix Web. From the documentation, our from request function should return the future type we define. We shall use the most basic struct that implements the future trait as our future type. This is the ready struct, which we import from the future module of the standard library. The ready struct is just like the resolve method in JavaScript promises. It is a feature that resolves immediately. The value in our ready struct is the result enum, whose OK value is this auth struct, which can be denoted as self, and the error will be the error type, which we shall soon define. If this token extraction fails, we want to return a custom JSON to the user. The error suitable for this is the internal error from the error module in Actix Web. We pass in the string type in place of its generic t. We rename this path variable to rec, and we get the request headers by calling the headers method of the HTTP request struct. We have an error here stating that we have an undeclared header module. So at the top of our file, we import the header module from the HTTP module in Actix Web. At line 82, we have an error that says it expects ready struct. We have to wrap the OK result enum in a ready struct. This can be done by passing this into the ready function of the standard library. Our error type is an internal error. We chose this error because we can construct it from a response. We pass in our error value in the ready function, and within the error value, we create an internal error from a HTTP response. For the cause of this error, we pass in the error string from decoding the JWT. Our response will be a HTTP response with an unauthorized status code and our usual fields. Since the first argument takes ownership of the string we passed, we clone this so that we can be able to use it for the message field. For the non-arm, we copy and paste the error arm. For the cause of this error, we set it to a string that says no token provided. We will do the same for the message field. We can now test this route. If we disable the authorization header, we get an unauthorized response and the message field says no token provided. If we generate a new token and pass in our auth, we successfully get the details of the user. If we modify this token, we get an invalid signature message. After waiting for 2 minutes for the token to expire and rerun the request, we get an unauthorized response with an expired signature message. The only protected route in our application is the secret view route, since it's the only handler that uses the auth extractor. Sometimes we may want to secure some routes without necessarily extracting the user from the request header. This is where middleware comes in. Axum gives us an easy way of implementing middleware from an already created extractor, which is the from extractor function. For example, if we nest some routes under the secret view route, we want all these routes to be only accessible by a valid user. We implement a middleware from the auth extractor by calling the route layer method at the end of the defined route. And in its arguments, we pass in the from extractor function in the middleware module in Axum. We then add the auth struct as the extractor type. Back to the Axum environment, we don't pass any token and call the /secret view /abc route. We get an unauthorized response. Passing in an invalid token or expired token won't work either. To view the content of this route, we have to get a token and set it in its authorization header. We can now see the content of the route without adding the extractor in its handler. Actix Web does not have this quick fix. Creating a custom middleware on Actix Web may seem overwhelming and complicated, but it won't remain the same after you understand how this transform and the service traits for creating middlewares work. So please like and subscribe with notifications on for incoming videos. Thanks for watching.